Hello friends, this is Dr. Shilpa Gawande. Today we'll discuss about the first order kinetics. In the last lecture we have discussed about the zero order kinetics. In that we have studied that zero order kinetics is totally independent of the concentration. Now in this lecture we'll discuss about the first order kinetics. In the last lecture we have seen that the basic equation, that is the dc upon dt is equal to minus k c raised to n. We numbered this equation as 1.4. Now as it is a first order kinetic, so putting value of n is equal to 1 in this above equation, we'll get this equation, that is dc upon dt is equal to minus k c raised to 1. It means it is dc upon dt is equal to minus kc, and we'll number this equation as 1.10. So from this equation we can clearly say that the first order process, it is the process in which the rate of reaction, it is directly proportional to the concentration of the drug. The rate of reaction, it is directly proportional to the concentration of drug. That means greater the concentration of the drug, faster will be the rate of reaction. And as there is a relation between there is a directly proportional, the rate of reaction is directly proportional to the concentration, so we can see that this first order process, it is a linear kinetics. It is a linear kinetics. So if we plot a graph, that is dc upon dt versus concentration, will get a straight line. See, this is a linear relationship. We can get it from the graph. Now we have this equation, that is dc upon dt is equal to minus kc, right? So rearranging this equation, if we rearrange this equation, so we'll get dc upon c is equal to minus k dt. If we integrate this equation, we'll get, that is the natural log c is equal to log of c0 minus kt, and we'll name this equation as 1.12. Now in this case, if we write this equation in the exponential form, we'll get c is equal to c0 e raised to minus kt. Now see here, e, what is e? It is a natural or Napierian log base. So in this equation we see that the first order process, it is, as there is only one exponent, so this equation, first order process, it is also known as the mono exponential rate process. And it is characterized by the logarithmic or exponential kinetics, that is the constant fraction. See, this is the constant fraction of the drug undergoes the reaction per unit time. That is a constant fraction of a drug, it undergoes a reaction per unit time. Therefore it is also known as the logarithmic or exponential kinetics. Now see, if we take a log to the base 10, the same equation we get, that is, we know natural log is equal to 2.303 into log to the base 10. So we get this equation, that is log c is equal to log c0 minus kt upon 2.303. So rearranging or by calculating this, we get log c is equal to log c0 minus 0.434 kt. This equation will name as 1.15. Okay. Now here you can see, if you plot a graph of percent concentration versus time, you will get a regular, that is a Cartesian plot. This is a regular Cartesian plot. And if we plot log c versus time, we'll get a semi-logarithmic plot, and that if we plot the semi-logarithmic plot, we'll get a slope, that is minus k upon 2.303 or 0.434 kt. This is the slope of this graph. So this is the equation for the first order kinetics. Now if we consider the first order half life, now we know that half life, it is the time required to reduce the amount to 1/2. So by putting the value of C is equal to C0.2 in this above equation, we get T half is equal to 0.693 upon T. Now here we see that the T half of the first order process is totally independent on the concentration, while in zero order process it was dependent on the concentration. But in case of the first order reaction, it is totally independent on the concentration. And examples, many of the absorption, distribution and elimination reaction, they follow the first order kinetics. So this was about the first order kinetics. Now we'll discuss mixed order kinetics also. Now what is mixed order kinetics? Generally what happens, many times what happens ki pharmacokinetic processes, they changes from first order kinetics to the zero order kinetics, and this change, if we take the if we increase the dose, or if we take the dose in the chronic diseases, in that cases this type of the things happen. So in this case what happens, the first order it changes to the zero order, and this type of the kinetics it is called as the mixed order kinetics. And as there are deviations from first to zero order, so rate processes get deviated, therefore it is also called as the non-linear kinetics. It is also called as the non-linear kinetics. And as it is dependent on the dose, this non-linear kinetics or the mixed order kinetics, it is also called as the dose dependent kinetics. And examples of these non-linear kinetics or the mixed order kinetics are the drug absorption, for example vitamin C. In case of the drug distribution, for example naproxen. In case of the drug elimination, example is the riboflavin. So these are the examples of the mixed order kinetics. So this is about the mixed order kinetics. And in some cases what happens, the non-linearity phenomena is seen when particular pharmacokinetic process it involves the presence of carriers or enzymes which are substrate specific or have a definite capacity, and that get saturated at high drug concentration, that is they are capacity limited. So such capacity limited process is they are also called as the Michaelis-Menten kinetics. They are also called as the Michaelis-Menten kinetics, which we'll discuss in the non-linear kinetics chapter. So this is about what the first order and the mixed order kinetics. So we should have an idea about this zero order, first order and the mixed order kinetics. So this is about the today's lecture. In the next lecture we'll discuss about the different compartment models. What are the types of the pharmacokinetic model, and in that types of the